Good day. I am George Wimberly, Director of Professional Development at the American Educational Research Association, AERA, and I'm pleased to welcome you to today's workshop, Cutting Edge Quantitative and Qualitative. Just a moment. Excuse me. Cutting Edge Quantitative and Computational Methods for STEM Education Research. This workshop is part of the AERA and Inter-University Consortium for Political and Social Research, that's ICPSR, our partnership for expanding education research in STEM, or what we refer to as PEERS. PEERS is funded by the National Science Foundation. Our PEERS Data Hub is a web-based platform, a convening place that enables discovery through wide-ranging forms of education and STEM-related data. It connects researchers to networks for collaboration and communication, and it promotes capacity building in research methods, data use, and responsible conduct in diverse forms of data. I encourage you to visit the PEERS Data Hub platform and become part of the Hub community. This workshop is part of a series in collaboration with the Institutes and Research Methods, IRM, which, like the PEERS Hub, is part of NSF's Building Capacity for STEM Education Research program. In this method series, the AERA ICPSR Hub features the 11 institutes that seek to promote research expertise in applications of computational, quantitative, qualitative, and evaluative research methods useful to STEM education researchers and broaden the STEM professional workforce. This is our second workshop in the series, and additional workshops will follow approximately each month throughout 2021. Today, you should have received an email message from us with where you can access the presentation slides that we'll have today. I want to go over just a few technical tips to help you as you view today's workshop. First of all, I want to thank our American Sign Language interpreters who are providing services for today's course, as well as our closed captioner. You should be able to see the ASL person on the screen, and you can turn on and activate the closed captioning. There are over 3,500 registrants for this workshop. So we all are in this webinar mode. So there are just a few things I think they're going to help make things a little bit easier here. First of all, we're going to take questions and the question answer box, the Q&A box. And this is for general questions at designated points. The instructors are going to be going through that box, responding to questions, but I'll also synthesize the questions and at designated times and ask them of the instructors. While we do have the chat box on where you are able to speak with the panelists, because there are 3,500 people on today, we're asking that you limit any comments in the chat box and not to use it for idle chit chat, so that we can follow. We're going to try our best to follow the questions in the Q&A box. Following the course today at 3:45 Eastern Time, our instructors are going to have an informal discussion where they were able to answer more questions. So what we're going to do is we're going to end at 3:30 Eastern, come back at 3:45. There's going to be a new link that we're going to provide for any of you who want to stay on and have an informal discussion with the instructors. We're thinking of this as had this been in person at the AERA annual meeting or other event that you would have had we've had a course, and then maybe you all meet later for coffee or somewhere in the hotel for more of an informal talk. And that will go on it'll start at 3:45 today. Also, with all good research, there's an evaluation. So following the workshop, you'll receive an email message asking you to complete a workshop evaluation. We're asking that you complete this evaluation as soon as possible. We all value your input and guidance as we develop future workshops and trainings. Also, today's workshop is being recorded. And this is you will all get a notification when this recording is available. We will do some editing and things too, but we'll make this available on the AERA website and the Peers Data Hub as well, where you'll be able to access the recording later. So again, we are pleased to offer this workshop, Cutting Edge Quantitative and Computational Methods for STEM Education Research. We have quite the illustrative faculty here that's just really stellar faculty that is prepared to give this course today, and we've given other courses at AERA and in our in-person series and some of our virtual courses as well. The faculty, Kenneth Frank, Guanglei, Stephen Raudenbush, Yanyan Sheng, and Kaitlin Torphy Kanaki from Michigan State and the University of Chicago. They are leading today's course, and we are grateful to the faculty leaders for sharing their expertise with us throughout this series. I can say so much about the faculty here and their expertise in statistical techniques and quantitative methods and all their major contributions that they've made to education research through their teaching, scholarship, research, and service to the field. You can always go online and find their vitas and to learn more about their work. All right, with that, I'm going to pass things over to Professor Kenneth Frank. Ken?
Thanks, George. We are excited to be here. We appreciate the Peers Network sponsoring this and NSF for supporting our work. I've got up here the list of people on the NSF grant, which you mentioned earlier, and you'll be seeing more of these people later on, and I'm just the first guy to go. With that said, I'm going to jump right in. This is the Cutting Edge Quantitative and Computational Methods for STEM Education Research. We have a website for this. I've got the link right here, and you can search for SciArm for STEM. And we are doing an NSF Summer Institute in Advanced Methods for STEM Education Research starting this summer. And what you're seeing today is sort of a sneak peek for that institute. The idea is to support a diverse cohort of NSF fellows, early and mid-career scholars doing STEM education research who want to learn about quantitative methods. And we want to focus on understanding the resources of unequal access to STEM learning opportunities and evaluating strategies for transforming STEM education to advance equity and inclusion. And I will say that we are still accepting applications. It is actually true that there are only a few spots left. We've got a great set of fellows already, but there are a few spots left. So if you go to that website and want to get the whole Summer Institute, you can go ahead and apply. So as behind what we're doing in terms of theories and methods, we're trying to investigate a complex phenomenon in STEM education, and that requires an ambitious research agenda. We want to be able to deal with competing theories and with scientific rigor. And so that's going to take us into what we plan to do. And in particular, we're going to we built our whole summer series and this workshop today around a hypothetical case of curricular innovation. So just picture this context. There's a new science curriculum that's aligned with the next generation science standards for urban high schools designed to improve science learning and reduce achievement gaps. And we might have various research interests associated with this. How is the new curriculum implemented? How do we think of the school as an organization during that implementation? Does the new curriculum work? Does it engage students? Does it lead to new achievement? Why does it work or not? For whom and under what conditions? So we might want to ask all those questions. And in terms of an orienting figure that we will use throughout today, the curriculum is over on the left. You've got some professional development represented on the bottom left, teachers getting professional development. And then that can lead to changes in teachers' practice and student engagement, ultimately leading to student learning. And this is just one sort of idealized hypothetical example. And the things that we're going to show you today are going to build off of this case study. You wouldn't do them all in any particular context, but the idea is to highlight what could be done. So if we take a research question, how is the new curriculum implemented? Does the new science curriculum increase engagement? We're focusing on the relationship between the curriculum and the implementation. We're just right here. We haven't gotten all the way to student achievement because this implementation and engagement occurs along the way. We might ask, what are the indicators of engagement? If we think about, does the new science curriculum improve student learning? That's all the way sort of the direct effect of the curriculum on student learning. Somehow, through all the things that the curriculum could change, it might affect student learning. That's certainly one of the questions we want to ask. Does the impact of the new science curriculum on student learning depend on the effectiveness of the professional development? So here, we're talking about the professional development. And that professional development may have been something that the district was going to do anyways, or it may have been part of the curriculum. But if it was sort of independent of the curriculum, we might say, well, how do these things combine? How do they interact to affect student learning? Or how does professional development moderate the effect of the curriculum on student learning? We might also ask, how does the new science curriculum potentially transform teachers' practice with support from professional development? So we might go to that intermediate step here and ask how these two factors interact to affect the teacher's practice. We can then also ask how the curriculum works through the teacher's practice to affect student learning, and that's a mediating mechanism of teacher's practice. And then finally, we could say, is there moderated mediation? That is, does the new curriculum improve science achievement through improving teachers' practice only if teachers have received effective professional development? So maybe this is an extra ingredient necessary, but the mechanism is ultimately mediated through teachers' practice. So you can see that even with this relatively straightforward, idealized case study, there can be a series of important and complex questions that we'd want to answer. I'm going to give you a little preview for where we're headed in terms of our methods. So the first is thinking about research design. Is random sampling feasible? Is randomization of the treatment feasible? Can you randomly assign schools, teachers, etc., to the new or old curriculum? If it's possible to randomize, would we think about a cluster randomized trial or a multi-site randomized trial? And we'll show you what those are in a moment. How about getting cross-sectional versus longitudinal data? Would we get one cohort or multiple cohorts? And that's a very important question right now, because any curriculum that is effective right now during our current days of the pandemic and other factors, social injustice, would that be effective a year from now in the same way through the same mechanisms? That would be an important question to ask. So we might think about multiple cohorts. So if we want to think about it as a multi-site randomized trial, if we are able to randomly assign people to curricula, we might think about within each school having a left and a right. Some of the teachers within a given school use the current curriculum, some use the new one. And then what we have is essentially randomized experiments in each of these school settings, and we can learn a lot about the heterogeneity of treatment effects in those settings. So that's one possibility. We might also think about randomizing at the school level and assigning some full schools to the new curriculum versus the current curriculum. And here we'd be treating the building as a whole, allowing the teachers to interact with one another, assuming they will, maybe even supporting those interactions. So treating the school as an organization. This is called a cluster randomized trial. We also are going to encounter measurement issues along the way, and Yanyan will be speaking about that in a little bit, but we've got some complex measurement challenges ahead of us. The enacted curriculum is what's actually done, not the beyond just the intended curriculum. We might want to know about that. In terms of teaching content, teacher content knowledge, we might want to know what this teacher knows, because that will affect the way they implement the curriculum. We'll want to measure the student-teacher relationships, and the curriculum could affect those relationships. We'll want to measure student engagement, and I think Yanyan's going to have a bit more to say about that. So we've got some very complex measurement challenges, even in this idealized case. if we just sort of allow ourselves to abstract the mechanisms, this is how we might represent the flow of what's going on. And we might, Guanglei is going to ask, is there moderation? That is, does the effect of the curriculum depend on the level of professional development? She's going to ask, is there mediation? Does the effect work through instruction and other factors, such as student engagement? Is there moderated mediation? Do these two things interact to affect instruction, which then affects student learning? Steve Raudenbush will be talking to us about multi-level settings. So within each school, you could have multiple classrooms. 6 are represented here. And that gets us thinking about the school as an organization, how the teachers in the organization and educators work together, the community context of the organization, how students within the school interact with each other. It makes us think about the agency of the teachers. So all those important issues will come up when we think about the multi-level aspect. I'll be talking about the social network phenomenon. So teachers' adoption of innovations could be influenced by the other teachers they talk to. And teachers might change who they talk to as they change their instructional practices. And so all that generates a very complex social dynamic through the implementation and during the implementation of the innovation. So you're not just implementing an innovation, but you're actually changing the social organization of the school. I'll be talking about that. And then Kaitlin Torphy, who is actually featured right here in this picture. She was teaching these kids on the south side of Chicago, and she will be talking about the role of social media and how that can affect teachers' practice, student engagement, ultimately through to student outcomes. And so here's what's coming. I've just been talking about this little preview, and Guanglei Hong will be talking a little bit more about the fundamental methodological issues in a moment for causality. And then Yanyan will speak about measurement, Guanglei to mediation, Steve to multi-levels. I'll come back and see you in a little bit on networks, and Kaitlin will talk about the computational methods and social media. And with that, I turn it over to Guanglei.
Thanks so much, Ken, for a great introduction. So many of the research questions that Ken has highlighted in the context of this idealized case study are actually causal questions. But this is not to say that descriptive questions are unimportant. You know, quite the contrary, a thorough description of a complex phenomenon is the basis for scientific discoveries. Yet whenever we try to explain a phenomena and try to intervene to produce desired results, the research questions inevitably become causal. So I'm going to introduce some basic concepts in the causal inference framework so that we all share the same language. So the purpose of having a framework is to discipline our thinking, not to limit our scientific imagination. So let me start sharing my screen. Just 1 second, I need to swap and get my spotlight as I need a finger to point at things. Oops. I think, sorry, I have to swap back because it's pointing at the wrong screen, right? How do I swap this again?
Display settings.
Display settings. It's covered by the toolbar. That's the problem. Sorry here. It's working now, right? All right. Sorry about that. So, well, to introduce everybody to the causal inference framework, which is having an increasing impact across many social science disciplines, as well as public health and medicine. The basic idea is quite intuitive. Let's start with looking at this little boy whose name is Julio. And one of the causal questions we had was about the impact of new curriculum on science learning. Let's ask this question about Julio. So think about if Julio would be taught with the new science curriculum, we would find out what his potential achievement score would be, right? The same boy, if he would be taught with the current curriculum, continuing the status quo, Julio's potential achievement score may or may not be different, right? So we take the difference between those two potential achievement score for Julio, that's the causal effect for this particular child. So that's the very basic definition of a causal effect for a single student, and it doesn't involve any modeling. Strictly speaking, you don't need to think about regression or whatsoever. So now we are ultimately interested in the causal effect for a population of kids like Julio. Sorry, I didn't make that work. So the potential achievement score for Julio, in contrast with the potential score Julio would have with new curriculum, as opposed to not having a curriculum, as opposed to having a current curriculum, that difference is the causal effect for this child. And when you have a population of students, it could be Tommy, it could be Jane, and then many others. Now we can imagine if all those kids in the population were taught with a new curriculum, we will have their population average potential science score, right? But the same population of kids, if continuing with the current curriculum, they would have possibly a different population average potential science score. So the difference between those two population average scores would be the causal effect. We call it the population average causal effect of the new curriculum on science learning for this population of students. So that's a definition. Now, you realize that for every student, such as Julio, you get to observe only one of those two potential outcomes. You cannot observe both, right? If the kid was taught with a new curriculum, you wouldn't be able to observe his score under the current curriculum, right? So because the latter would be counterfactual. So the indication is now, how do we want to find out the counterfactual quantities, which is essential for finally identifying the causal effect? And it involves relating the counterfactual quantities to the observed quantities, or using observed quantities to approximate those counterfactual quantities. Now, this would involve key assumptions, because eventually the counterfactual quantities cannot be directly observed. And those assumptions that you have to invoke often cannot be empirically verified. So that's the difficulty. And which assumption to invoke depends on the research design. Ken talks about, ideally, if you can run a randomized experiment, the assumption that we require would be relatively weak. Without a randomized experiment, you can still try to answer these causal questions, but you will have to invoke much stronger assumptions. When we say assumptions stronger, meaning they may not hold. And if the assumptions fail, then the causal effect is not identified, which may not necessarily be the end of the world, because this is a time when you can assess, if there's a hidden bias, how large the hidden bias might be, and is my initial result sensitive to such a hidden bias. So that's the question for sensitivity analysis. So now, considering in a quasi-experimental study, we will be worried about the selection bias, because the observed quantity you have may not be equated to the counterfactual quantities you need for identifying a causal effect. So consider, let's say in a quasi-experimental study, teachers who sign up to implement a new curriculum tend to be the ones who are more motivated and more skilled. And those are the teachers, the students under the new curriculum are more likely to be exposed to. And the teachers who chose to stay with the current curriculum are more likely to be, say, less motivated or less skilled. So when you compare students taught with the new curriculum and those who are taught with the current curriculum, the two groups may differ in the composition of the teachers So this pre-existing difference would give rise to selection bias. It will make the new curriculum looks better than the current curriculum, primarily because the teachers who are using the curriculum appear to be more motivated and capable. So this is a graph illustrating the problem here. And we are showing the distribution of teacher quality, say, in the entire population. Along this dimension, on the top, we have teachers who are having a higher quality, and the bottom are those with lower quality. And let's say, in a quasi-experimental study, teachers who are implementing a new curriculum, they tend to, in this group, we tend to have an overrepresentation of teachers who are of relatively higher quality. And among those who are continuing with the current curriculum, there's an overrepresentation of teachers with relatively lower quality. So it just shows that there's a pre-existing differences between the two groups, and neither group resembles the overall distribution of teacher quality in the population. So this problem can be solved through randomization, because if you flip a coin to decide which teacher is going to be in the experimental group, implement a new curriculum, which teachers will be in the current curriculum, every teacher will have an equal chance, right, to be assigned to the treated group. And therefore, it guarantees that the treated group and the control group will have the same distribution of teacher quality as what you would see in the entire population. So what if a randomized experiment is infeasible? And we said, you can still try to proceed with a quasi-experimental study. Now, but you have to take great care with trying to remove selection bias, such as bias associated with pre-existing differences between two groups in teacher quality. So we'll say, if we can make an assumption that the measures of teacher quality are the only confounders of the curriculum impact on student learning, there are two ways to go about it. I will summarize them as two different rationales of causal inference. The first is to pool conditional mean difference. This can be done through multiple regressions, through propensity score matching, or stratification, or covariance adjustment. A variety of methods, they all use the same rationale. The rationale is to find teachers in the experimental group and the control group who have similar quality at the baseline. So it can be viewed this way. Let's say there are 5 levels of teacher quality from low to high. And at each level, we find the teachers from the treated group and the control group who are at the same level of teacher quality. And if you compare student learning within this level of teacher quality between the new curriculum and the current curriculum, you will have an estimate of the curriculum impact on student learning that is no longer confounded by teacher quality. So this is done at within each level of teacher quality, and then you can pool the results across all these levels, right? So it's called, the rationale is called pooling conditional mean independence. Now that's not the only way to proceed. A second rationale, under the same assumption that measures of teacher quality are the only confounders, you could try to transform the pre-treatment composition of teacher quality of the treated group as well as the control group through weighting, such that both groups, after weighting, they will have the distribution of teacher quality very similar to that in the overall sample. So here's the idea. We notice that the two groups have their teacher quality distribution different from one another, different from the overall population. So we can apply weight. We notice that in the treated group, teachers of higher quality are overrepresented. Let's give them a lower weight, right? Teachers of lower quality are underrepresented in this group. Let's give them a higher weight. And then through weighting, we can transform the distribution of the treated group such that you will have the same distribution of teacher quality as that in the entire population. And we can do the same with the control group. Similarly, teachers of higher quality underrepresented, give them a higher weight. Teachers of lower quality overrepresented, give them a lower weight. So after weighting, the weighted treated group and the weighted control group will have very similar distribution of teacher quality, similar to what you would see in the entire population. Therefore, the weighted sample would approximate a completely randomized experiment. So those are the two rationales, and they both can be used to identify the average causal effect of the curriculum on student learning, removing the confounding impact of teacher quality. So now we have carried out these strategies under the assumption that the teacher quality is the only confounding source of confounding. So this is similar to say that the assumption is there are no unmeasured confounders, there are no omitted confounders in this analysis, right? So who believes that? Like Alexander Hamilton would say, they will never be satisfied. It's a very, very strong assumption in your quasi-experimental study. But as I mentioned, that's not necessarily the end of the world. You have to think about what are the omitted confounders and how large the bias would be associated with the omitted variables. So that comes to the question about sensitivity analysis. So after we have adjusted for teacher quality, sensitivity analysis is aimed to examine the potential impact of omitted confounders and how that might change our initial causal conclusion. So we're saying, we have the analysis is based on a comparison between the observed science learning of students under the new curriculum and the observed science learning of students under the current curriculum, right? Those are observed data after we have adjusted for teacher quality. Yet the difference between the two may not be equal to the causal effect of the impact on student learning. The causal effect, as we said before, is defined as the difference between the observed science learning under the new curriculum and the counterfactual learning under the current curriculum for the population of children, right? And we're talking about the same population of children. Yet the observed data we obtained from students under the current curriculum, they might be different from the kids who were using the new curriculum. If there are remaining difference between the two groups that are pre-existing, that would give rise to bias. So for example, if the kids who are using the new curriculum tend to have a more adventure background than the kids who are using the current curriculum, the bias will sneak in, right? It will make the new curriculum looks better than it really is, even after you have adjusted for teacher quality. So while the causal effect is A minus B, the bias is B minus C. The observed quantities give you a contrast between A minus C, right? It's the sum of effect and the bias. So the larger the bias, the more shaky the initial result would be. So we'll say if pre-existing differences between the treated group and the untreated group remain, then you will have a non-zero bias. So the sensitivity analysis is trying to determine if the bias is relatively large relative to the effect, then the causal conclusion is likely sensitive to the omitted confounding. And we can view this, again, an image from Ken's sensitivity analysis talks. So think about student SES as an omitted confounding variable, omitted from the initial analysis. And let's say students from a higher SES background are overrepresented in the treated group that used the new curriculum, and underrepresented, of course, in the control group using the current curriculum. So there is a positive association between SES and the adoption of the new curriculum. And we all know that SES tends to be positively associated with student achievement, right? So that will introduce a positive bias, will inflate the achievement of science learning achievement of students in the treated group in comparison with the control group. So a sensitivity analysis is asking two questions. Number one, how large would a hidden bias need to be to alter the initial conclusion? And the second, is such a hidden bias scientifically plausible, right? You might need a very large bias to alter the initial conclusion, but your conclusion may not be sensitive if such a bias is not very plausible. So just to make sure everybody is staying on the same page, we have a poll that will ask you two questions. We'll ask you to fill in the blanks. The first question is, a causal conclusion is considered to be sensitive if a relatively small or large bias will lead to a qualitative change in the conclusion, because such a hidden bias is highly plausible. Do you put in small or large? The second question, conclusions that are harder to alter by hidden bias are expected to add a lower or higher value to scientific knowledge. You're going to choose between lower or higher. So let's ask our technical staff to launch the poll if you can. And everybody will take maybe 30 seconds to choose your answer. Do I need to stop share so you can launch the poll? I'm sorry, I don't have control of the poll, so we have to ask.
It is coming right up here.
Oh, it does. Great. Thank you. Well, it gives everybody a second to think about it. I think we can close the poll if you could share the results with all the attendees. Interesting. So 61% of people select small to the first question. 32% said big bias. And the second question, the majority, 69% said higher value, 24% said lower. Great, thanks. Let me go back, share the screen again. Right, so let's revisit first question. We are talking about a hidden bias that is highly plausible. What kind of bias is more plausible, small or large? Right, a small bias is more plausible than a large bias. And if a causal conclusion can be changed by even a very small bias, it's sensitive to a small bias. That's the case, when we have to worry, right? This kind of conclusion is more sensitive because it could be easily changed by even a relatively small amount of bias. If it takes a large bias to change a conclusion, that conclusion is considered to be less sensitive because large bias is less plausible. And the second, conclusions that are harder to alter by hidden bias are expected to add a higher value because such conclusions are less sensitive to hidden bias. So that's the reasoning that you would bring into a sensitivity analysis, into judge on scientific grounds, how large the bias needs to be, and is it scientifically plausible? So I'll conclude here, and I'll shift to the last slide of this part and ask Ken to tell us some information about the sensitivity analysis that he has taught in the past.
Thanks. The AERA has also sponsored a virtual learning series, and I've did a workshop on that on sensitivity analysis called "What Would It Take to Change Your Inference? Quantifying the Discourse about Causal Inferences in the Social Sciences." And in that workshop, we would learn to generate statements such as X% of the estimate would have to be due to bias to change your inference, or a confounding variable would have to have certain properties to change your inference. And Guanglei, if you hit the page down, just to add one more thing to that, I think.
This
one? Click on that, yeah. Then there's an app for this, and you can put in an estimate and a standard error and a sample size, and it will generate certain statements for you. And so go ahead and try the app as you like, and I'll put the app into the chat. Thanks. And that is where we wanted to stop with this introduction. And we have some time to take a few questions.
Great, great. Thank you both for those presentations. One thing that has come up, Dr. Hong, is that there have been a lot of questions in the chat about how you're measuring teacher quality. Can you speak to that a little bit more about how you're measuring teacher quality and weighting in issues around teacher
that
quality?
Question is so timely. Actually, that is the question that Yanyan is going to talk about. The next topic is about the measurement. So I don't want to steal her show.
Okay. Great. Well, I'm looking here, though. There are a lot of other there are other questions that have come up that are more about your institute. And I just want to say to the audience that they can contact you directly and to talk about applying to your institute. So
yes, they may visit our website, and there's contact information on the website as well.
Okay. Well, with that, could you also talk again about, repeat a few things about an example of small bias in the curriculum?
Example of a small bias?
Yes.
Well, it could be that, after you have adjusted for teacher quality, let's say teacher quality tends to be associated with student SES, right? Let's say, students with higher SES may have a better opportunities, to be taught by teachers of better training and with greater resources, right? So it could be that after you have adjusted for teacher quality, the remaining bias associated with student SES could be relatively small. And the small bias is not going to change your result that much. Right? If you find, the initial causal conclusion suggests that a causal effect is, say, half a standard deviation after you have adjusted for teacher quality. And the hidden bias associated with student SES is going to change your effect size by, say, 10% of standard deviation. And after this further adjustment, you still have 40% of the standard deviation as your effect size, right? So it doesn't necessarily change your initial conclusion. In that case, the SES, even though omitted from your initial analysis, is associated with a relatively small bias. And your initial result, your conclusion will stay insensitive to such an omission. Does that make sense?
Great, thank you. Can you give an example of something that's highly plausible?
I think SES is a quite plausible bias, based on past literature. You want to take into account all the pre-existing differences between the treated group and the control group in what kind of students they serve. But Ken may have other ideas as well.
Well, I was going to give an example of something that's not plausible. So sometimes somebody will say, well, you didn't control for eye color. Well, really, would eye color really change affect achievement or have a relationship with the treatment? So that's the kind of thing that, you know, there's some things that are reasonable, plausible, reasonable, that we should be discussing. And the sensitivity analysis helps us weed those out and identify the ones that might really be important.
Yeah, and I can add to that, you know, we say, you know, how large hidden bias could possibly be, right? In the education literature, we understand that students' pre-test score tends to be the strongest predictor of the post-test score, right? And it's hard to think of any other predictors of achievement more important than the pre-test score. So if you have already adjusted for pre-test score, which could, you know, predict your treatment and predict your outcome, it's hard to find something that can rival it. So that would set the upper limit, upper bound for how large, you know, is a bias possible.
Great, thank you. I think that's all the questions we have, or time we have for questions. And there will be time at the end of all the presentations for further questions and discussion.
Okay, my name is Yanyan Sheng. I'll be next to present to you about measurement considerations necessary for the stylized case that Ken has introduced, and also Guanglei has raised that teacher quality. How do we measure that? So let me start sharing my screen. So getting to the theoretical model that you have seen previously from Ken's introduction, basically the goal is to evaluate student learning. The learning outcomes such as achievement can easily be measured by actual classroom grades or school reported GPA or large-scale standardized testing. Whereas more challenging is with assessing such constructs such as teachers' quality, teacher-student relationship, and or student engagement. So my presentation is more focused on the student engagement, but definitely the measurement issues apply to the measurement of teacher quality. So basically, how do we construct a theoretically grounded instruments with strong psychometric properties to measure student engagement in science learning, especially? As many of us know, that measurement basically starts with operational definitions, which are very requiring a thorough review of the literature. So without getting into the complexity for measuring this construct of engagement, let's just assume that we define simply the engagement, student engagement, as cognitive engagement, which is simply students' psychological investment, such as concentration during science learning by, and then we start construct self-report measures as what traditional practice has been. So with the literature, people have found that the self-report measures are usually easy to collect information, but do not actually capture engagement-related process in real time, because oftentimes we give students survey questionnaires asking them to respond to particular engagement level with respect to activities that they have done before. So therefore, this kind of measures may oftentimes involve undesirable amount of random error. And this kind of measurement error will have some effect that is illustrated in the slide on the two plots, where you see that this plot on the left is reflecting engagement. Let's suppose that we could be able to measure that. We measure engagement with no measurement error. So basically, this is for that scenario, perfect scenario. There's no measurement error. Whereas the plot on the right is for the situation where engagement is measured with quite a bit of random error. So if it happens, then the amount of random error or measurement error results in the unexpected, undesirable bias, and also large extended errors, as you see reflected in the 95% confidence intervals, for using this engagement measure for predicting whatever outcome variable that we have. For example, if the outcome variable is achievement, or if the outcome variable is of a criterion that we want to establish criteria-related validity. So then we have bias in this case, as well as large standard error. This scenario can be reduced or can be resolved by adding more similar items, as you see in these two plots. The plot on the left is involving only one item that is having quite a bit of random error or measurement error. If we add multiple items that are similar and also correlate to a certain level, and then we see that the amount of bias as well as the imprecision that is reflected in the confidence interval gets reduced in predicting the outcome as well as the criterion variable. By doing that, one has to be really careful of using sum scores, especially for the situation where the sum total is for items that measure subdomains that do not highly correlate with each other, such as the deep engagement and the shallow engagement that have been used for measuring cognitive engagement. They have been found to correlate at a level of 0.3. So if we combine these two scales or these two aspects, and then the sum score is often ignoring the two dimensions and then treating these two, resulting these four people to be exactly the same. Whereas in actuality, we have ignored some important factors or dimensions. So we have to be careful with that. In constructing self-reported measures, especially for, say, for example, cognitive engagement, our goal is to use as few number of items as possible to measure as many aspects of the construct as possible. So as reflected in this plot, as you see that, let's assume that the square is basically representing the construct that we are interested in measuring, cognitive engagement in our example. So ideally, we want items, each circle represents items to be overlapping to a certain extent that they cover the entire range, entire space or entire domain. The reality, however, is that oftentimes we have highly redundant items that fail to cover much of the domain. Basically, for this middle plot that demonstrates. So it's easy for us to reduce the number of items to come up with a test with fewer number of items that cover the same number of domains, like what we see on this plot on the right. The real challenge is to try to include items or indicators that cover the entire domain. So there's that need of define the content domain, and also the need of the use of experts in establishing the content validity of the measurement. So if we are thinking about start constructing self-reported measures for measuring cognitive engagement, as what we said before, cognitive engagement is defined as psychological investment in learning, especially in science learning. Let's take a quick look at a few items and see whether they are appropriate for this kind of environment for measurement. First item on the slide that you see is that I'll learn, but only if my family or guardians give me a reward. And this item is obviously, as you see, is not an engagement item. It's really a motivation item. So it's not appropriate for including in our measure. Looking at another item, when I am in class, I listen very carefully. So basically this item is involving a behavior of listening carefully, right? So it's basically, again, it's not a cognitive engagement, it's for behavior engagement. So in that sense, it's not appropriate for the measure that we want to construct. Item number 3, I enjoy learning new things in class. Is that appropriate for our instrument? Probably not, because this item says that I enjoy, so there's that enjoyment. So that enjoyment is more related to the emotional aspect of engagement, but not really cognitive or psychological aspect. So this is not really an appropriate item either. Looking at that last one, I find that reviewing previously solved out problems to be a good way to study for a test. So this is potentially definitely a good item that's possibly available or possible for our self-reported measure for measuring cognitive engagement. So if we going with this fashion to construct our measure with many items similar to this, to construct our measure for measuring cognitive engagement, we will have to be aware that such measures that we have created with these kinds of different items, similarly measuring the cognitive engagement, they may be performing differently based on the task or context or grade level. And then we need also to be aware that the traditional or classical measurement is for the situation where the students' engagement level depends really on how engaging the task is. So if students are dealing with less engaging tasks, and their engagement level is definitely tends to be low. If students are basically dealing with more engaging tasks, and then their engagement level tends to be high. In addition, we also need to be aware that the item that we include in our measure will be sample dependent. So take a look at this item again that we were looking at previously. This item was actually taken from that questionnaire of attitude toward math. So if we are given this item to a group of people, students who are very math oriented, and the item may have characteristics that have that might be very different from those when this item is given to a group of students who are less math oriented. So so ideally, whenever we create our measurement, we would like the items and the students to be placed on the same engagement continuum. Pretty much like this plot shows, from low to high, so that we can compare persons with items, and items and with persons, they will be scaled on the same scale. And this is basically the advantage of a more modern aspect of measurement that's called item response theory. So in general, certainly the measurement of student engagement is not as simple as simply cognitive engagement, or as simple as what we have gone through. The real challenge in measuring constructs such as student engagement lies in the definition of the construct itself, and how to measure the construct. Over the past 20 years, researchers have studied the student engagement, especially in science learning environment. And then they decided that science engagement can be categorized into these different categories, reflecting that this construct is definitely multidimensional. And so we have to be really careful whenever we are studying student engagement, and we need to decide how engagement is defined in the context of the particular problem. And we also need to choose a specific method that can measure the aspects of the phenomena that we are interested in. In a recent special issue, Sinatra and her colleagues has this special issue devoted to student engagement, where they have demonstrated the use of, aside from self-report measures, they have demonstrated the use of computational methods, as well as social network analysis, which you will hear later in our webinar, how they have been utilized for measuring science engagement. So if you are interested in learning more about science engagement, definitely feel free to check out that special issue. But that's all I want to talk about regarding the measurement considerations for measuring complex constructs such as student engagement in science learning environment. So I want to stop here for any questions.
Okay, great. Thank you so much. Well, can you say a little bit more? You started to talk about self-report. So
Yes.
there's a question about how do you account for self-report measures where the error may be random, but not systematic?
Oh, that's a good question. So for well, we just assume that that's basically random error, but definitely there could be systematic error that we'll have to take into consideration, because with the self-report measures, really it's depending on the students' recollection of what their engagement level with the activities that they are involving in, right?
Thank you. Another question is, how would you represent a multidimensional construct?
Well, the multidimensional construct will have to be measured using multi-dimensions. So what really, if the dimensions for the construct that they are not highly correlated, I wouldn't think that we should combine them. So what we need to do is we will have to use multiple subscale measures for explaining that particular construct, such as the student engagement. It's not a single dimension, so it could be going in multidimensional. So we'll have to measure the multidimensionality using different aspects or different domains.
Can you also speak a bit about using IRT, item response theory versus classical Roche theory?
Oh, classical Roche. Well, the Roche model is a special case of the item response theory, where the slopes are basically fixed to be assumed to be the same. So basically, for the Roche models, the item difficulty levels or location parameters will be allowed to be different, whereas the discrimination parameters will be fixed to be the same. So other RT models, like say, for example, the 2-parameter model, the 3-parameter model, they can allow the items to differ by the discrimination parameter or by guessing parameter if there's random guessing involved.
Great, thank you.
Sure, you're welcome.
I think there's one other question that questions are coming in now here. I guess this is another question about going back to self-report and generalizing self-report results. What's the best way to generalize those results in a group that you've sampled?
So if I understand correctly, what the question is asking, what is the best way to generalize the self-report results, right?
Yes.
Well, with the self-report, definitely we'll have to assume that the students' response are accurate. But then definitely, as I mentioned, or especially with the studies or research with the student engagement, people have found problems with self-report because there's some potential problems, especially with the engagement, because it's not capturing the students' engagement in real time. So some researchers have looked at other methods for measuring engagement in situations. So basically, they ask the students to carry out a task, and then they measure the eye track. So that's basically a different aspect of measurement. It's not relying on survey questionnaires, but relying on some other tools to measure. But so getting back to the question, how do we summarize the results? I would think that we definitely always want to report the results of the self-report with other methods of measurement, such as the tracking, such as the interview or observations that teachers can do with the students' engagement level. So I hope that answers the question.
Thank you.
Absolutely.
Thanks. So I think that'll be our last question for this segment. I think we're going back to Dr. Han. Guanglei.
Hi. All right. So lively discussion about measurement, a great amount of interest there because exactly because how important the topic is. So I'm going to switch to another topic no less important, I hope. It's about the causal mediation analysis. Let me make sure I can share my screen successfully this time. Got my spotlight going. Okay. Yeah. So in the overview part, we discussed a whole set of causal questions, starting with a very simple one. Does the new science curriculum improve student learning, right? A lot of the IES-funded studies are trying to answer the question of what works. Does the curriculum actually work? Now, more complex questions, more important, equally important questions can be asked. Does the impact of the new science curriculum on student learning depend on the effectiveness of professional development? And as Ken pointed out earlier, this is a question about moderation. Does the causal impact is the causal impact moderated, right? Is the causal impact of the curriculum on learning moderated by the effectiveness of professional development? So here, professional development served as a moderator. And you would also want to know, by the way, moderation is important because, in a case in which you find that the curriculum doesn't seem to have an impact as great as you had initially theorized or anticipated, it might be because the professional development was lacking, so the moderator may provide an answer to that question. And you will also want to know, does the new science curriculum improve student learning through improving teachers' practice, which is probably what people who developed the intervention, developed the curriculum had anticipated, that the teachers' practice, teachers as agent are the ones who deliver the curriculum. And that's the key step through which the curriculum could affect student learning, right? So that's a question about the mediation. Is instructional practice an important mediator, as one may have hypothesized? And therefore, in this case, if the curriculum is not impacting student learning, you would wonder, is that because it failed to change the teacher's practice, right? Or maybe the teacher's practice has been changed as intended, but somehow it failed to affect student learning. Maybe it's the second link that is lacking. And lastly, you may also ask, this mediation process, curriculum affect student learning through teaching practice, could that be dependent on professional development? We state the question as, does the new curriculum improve science learning through improving teachers' practice only if teachers have received effective professional development? So that's a whole set of questions. I'm just repeating what we have introduced in the overview part. But now, and Yanyan has talked in great length about how, all the issues you need to consider when you try to measure things as complex as instruction, regard to what teachers do and how students engage. So by the way, what I mentioned earlier, when you have a mediator and a moderator, and then the mediation process can be moderated, it's called moderated mediation. So now there has been persisting confusion about the distinction between moderation and mediation, just as the confusion we have seen around causal analysis versus a causal analysis, not just a typo. So that's what I'm going to focus on, more on the mediation part. So, but first of all, what is moderation? A moderation analysis has its goal. It's trying to examine for whom and under what conditions an intervention works. So the moderation analysis is aimed at revealing heterogeneity. We understand that people are not all the same and the settings are not the same. So we want to see whether there's a heterogeneity in a relationship and whether the relationship could be altered in direction or in strength by different levels of a moderator. Now, what is mediation? Mediation is quite different. A mediator explains an intermediate process that transmits the intervention impact on an outcome, right? Even though what works clearinghouse, is intended to tell you whether the intervention works in changing this outcome in the desired direction, but what's happening in between. So a mediation analysis answers the theoretical question of why. You don't just leave the intermediate process in a black box. You want to open up the black box, especially for understanding if the intervention works, why so, right? If it doesn't work, why so, what happened in this process? So for example, we use this past diagram, everybody is perhaps familiar with, to just illustrate the mediation story here. The key mediator is instruction involving teacher-student interactions around the content materials. Let's say the theory states that here's what happens inside the black box. When you have a new curriculum, it is designed to improve student learning through providing additional opportunities during instruction for teachers to engage students in the process of scientific inquiry, rather than just delivering the scientific content simply as given. So in other words, the new curriculum is replacing the curriculum with the hope that instruction will be changed accordingly, such that there will be more inquiry-based instruction rather than just teachers delivering content as it is. So that's the theory. How do we empirically examine this theory? You have to explicate your theoretical hypothesis, right, that can be empirically investigated. So one question could be, would a new science curriculum potentially transform instruction? Is there a link, is there a causal effect of the curriculum on instruction? And you want to know, would a new curriculum affect student learning through transforming instruction, maybe as hypothesized initially, right? Is there an indirect effect of the curriculum on learning transmitted through instruction? And you will also be interested in whether the new curriculum affects student learning without changing instruction, right? Is there a direct effect of the curriculum on student learning? So we use these words all the time conceptually. So this past diagram is convenient for illustrating the conceptual framework, the conceptual relationships. But that's not how this doesn't tell us how these causal effects, indirect effect versus direct effect, are defined. Right, and we earlier we talked about how you define a causal effect. So, for example, the effect of the curriculum on student learning, we call the total effect of the curriculum on learning. It's a contrast between two potential outcomes for each child and for the entire population of students. So we're contrasting potential student learning under the new curriculum with transformed instruction, with more scientific inquiry that is aligned with the curriculum, as you would see in this picture, right? So we want to assess potential student learning under this treatment condition. And this is to be contrasted with potential student learning under the current curriculum with untransformed instruction, in which the teacher is delivering the scientific content as it is, right? So the difference between two defines the total effect. Now, what the mediation analysis is trying to do is to decompose this total effect into an indirect effect and a direct effect. The indirect effect is the impact of the curriculum transmitted through a transformation of instruction. So that would require that we bring a third potential outcome, which is potential student learning. Under the new curriculum, students are using the new curriculum, yet teachers fail to transform their instruction. You know, this is something conceived in a counterfactual world. And although it could happen in reality in some of the classrooms for sure. So the contrast between the first two potential outcomes is when the curriculum is new, yet we are contrasting transformed instruction with untransformed instruction. And any difference that would result in student learning is the indirect effect, right? It's the indirect effect of the curriculum transmitted through the instruction on student learning. So any difference is to be attributed to the difference in instruction, not in the curriculum itself. And the remaining part is a direct effect. That's the contrast between the second potential outcome and the third one. Here, we are asking if the curriculum is changed from the current one to the new one, yet counterfactually, the instruction is remaining untransformed, right? That difference between the contrast between these two potential student learning outcomes is to be attributed to curriculum change that is not transmitted through instruction, right? It has to be transmitted through other unspecified pathways. So that's a direct effect, and an indirect effect and direct effect would add up to the total effect. So that's how the decomposition is done and how these cause effects are defined in terms of potential outcomes. And we know that some of these are counterfactual, some can be observed. So to view this visually, think about, remember Julio, this lovely boy. If Julio and his other students in the same population were put under the new curriculum along with transformed instruction. So we're using we're using quality of instruction. The quality of instruction may have, in this case, has been transformed by the new curriculum. And in this environment, we will have the student learning displayed by Julio and other students in the population. And then this is to be contrast with same kid with same other students in the population, yet under the current curriculum in which the instruction has not been transformed, right? The contrast between those two is the total effect. But we have brought in a third scenario, a third potential outcome. This is when Julio and other kids are using the new curriculum, yet the teachers didn't transform their instruction, right? So if the instruction was not transformed as before, at a higher end, we have instruction of higher quality, and at the lower end, we have instruction with lower quality, right? If the instruction was untransformed, more teachers will be teaching with relatively lower quality, right? So in this kind of factual world, with a new curriculum, with uninformed instruction, untransformed instruction, we will see the student learning results of all the children. So we mentioned that the contrast between these two scenarios, that defines the total effect. And the contrast between these two, using the new curriculum, yet the quality of instruction differ between these two scenarios. That contrast is the indirect effect. And if the curriculum has been changed, yet the instruction remains the same as it was under the current curriculum, that contrast gives us the direct effect. So then the next question is, how do you, the definition is fine. How do you identify that, right? Especially that the middle quantity seems to be counterfactual for almost all the kids. Not necessarily. Some kids might be using the new curriculum, yet the teacher didn't change their practice. So it's not entirely counterfactual. So if you remember before that, I mentioned two different theoretical rationale in causal inference. It would apply here as well. So one strategy is to identify these causal effects through pooling conditional mean difference. So let's focus on the direct effect, right? The direct effect is we change the curriculum, but if instruction remain unchanged. So let's divide the qualitative instruction, which is our mediator, into 5 levels, just for convenience. And within each level, right, we have the treated group and the control group. They're using different curriculum, yet their quality of instruction would be comparable, right? So within each level of quality of instruction, if you compare the experimental group with the treated group with the control group, that difference in student learning on average is an estimate of direct effect. So you can, of course, pool the mean difference across all different levels of the mediator, right, to obtain an overall estimate of the average direct effect. So that's one approach. And you can do this, people have tried to do this through regression more often than using other methods. By the way, conventionally, direct effect was assumed to be equal across different levels of mediator. That assumption doesn't have to hold. So in a new method, they have relaxed this assumption, which is very important, major progress. And in addition, we could try to identify the causal effects through weighting, as I suggested earlier. So we understand that the treated group and the control group differ not just in the use of curriculum, the curriculum that has been adopted, but also in the quality of instruction. The mediated distribution differs between the two groups. And the middle world that we need for decomposing the total effect, this total effect into indirect, direct effects, is a world in which students are using new curriculum, yet are still exposed to the untransformed instruction, right? So we can do this through weighting. We can weight the treated group, mediated distribution in the treated group, such that they will display quality of instruction similar to the distribution we see in the control group, right? What you do, you just downweight in the treated group those teachers who are displaying high quality of instruction and give a higher weight to teachers who are displaying low level of instruction. And then you can compare the weighted average student learning with the control group student learning, right? That difference is the direct effect. So that's the second rationale, and I hope it's relatively intuitive as well. So these are the identification strategies, and you apply it to sample data, you obtain sample estimates. So next, I want to alert everybody to a number of issues that I think are very important, but there has been some misconception in the past. Oh, by the way, I should mention that the nice thing about the weighting is it's unconstrained by scale of measurement. The mediator can be measured as binary, continuous, multi-category, ordinal, multinomial. There's no constraint when you use weighting. And there's no need to specify an outcome model. Whenever you specify an outcome model, writing down Y as the outcome as a function of the treatment as a mediator, and you have to control for covariates, you can easily misspecify the model, which could lead to bias. So weighting avoid all these issues. So, so a number of questions for the audience. Question 1, does treatment randomization guarantee causally valid mediation analysis? If who uses the new curriculum, who uses the current curriculum is a result of randomization, right? So there's nothing that would confound the identification of the total effect of curriculum on student learning. Does that guarantee that your mediation analysis will be causally valid as well? Well, the answer is no. Because even though the treatment is randomized, the mediator is not. Because the mediator is not randomized, it's an intermediate outcome of the treatment. And people can exercise their self-selection at this intermediate stage, right? So the mediator outcome relationship can be confounded, even though the treatment effect on the mediator is unconfounded and the treatment effect on the outcome is unconfounded. But the mediator outcome relationship can be confounded by baseline characteristics of teachers, for example, teacher motivation and the teacher's content knowledge for teaching, right? If teachers who are more motivated, have better content knowledge at the baseline, are more likely to change their instruction, or vice versa, it could be the opposite. And so these baseline characteristics of a teacher would predict quality of instruction, would also predict student learning, right? So it will confound the media outcome relationship. So it will require that we make adjustment for these confounders. It's essential in causal mediation analysis. So you could adjust for selection bias associated with these confounders, either through pooling conditional mean difference or through weighting. As I mentioned earlier, you can combine, what I discussed during introduction to basic concept of causal inference with, these strategies when applied in the context of causal mediation analysis. So that's the first question. Second question for you. Should the total effect be non-zero before you proceed with a causal mediation analysis? What if I found a curriculum doesn't work, right? What if the total effect of the curriculum on student learning is zero? Do I still need to conduct causal mediation analysis? Would that, generate any new knowledge? I think in the past, many researchers were misled in thinking that if the total effect is zero, that's the end of the story. I'll stop there. The answer is no. You shouldn't stop. The total effect doesn't have to be zero. Doesn't have to be non-zero for a mediation analysis to be valuable. So because mediation could occur even when the total effect is zero. So I'll give you two scenarios. Number one, the hypothesized mechanism might be offset by unexpected side effect, which we know could happen quite often in medicine, in education as well. Let's say, we hope that new curriculum would positively affect the quality of instruction, which will positively affect student learning. But what if you put too much burden on teachers having to deal with everything they were already dealing with, right? All the paperwork, all the issues with management, class management, and issues that come with students' families. On the top of this, they have to, handle new curriculum. You could have teacher burnout, right? That is an unexpected side effect. When you have a positive indirect effect and a negative direct effect, that could lead to a cancellation of the indirect effect and direct effect, leading to a total effect. So understanding this underlying mechanism is important to help you improve the curriculum, improve the support for teachers, right, to enhance its positive effect. Another scenario, the treatment could be beneficial to some, but detrimental to others. Or it could be beneficial under one condition, but detrimental under another, right? That's a question about the moderated mediation. The mediation process may differ across subpopulations of individuals, may across different settings. And that's important to know as well, even though when you look at the overall average, the total effect is zero, but it's not zero for different groups under different conditions. So identify those conditions and figure out what are the conditions necessary to make the program work is also very essential. So that was the second question. The third question, should the mediated outcome relationship be constant? So people who have conducted mediation analysis, typically you have used conventional methods and you're familiar that such methods assume that the treatment-mediated relationship, which is denoted with A, and the mediated outcome relationship, denoted with B, and then these are, causal in nature in causal mediation analysis, right? And each of these two causal effects are typically assumed to be constant. And because they are both constant, then A and B are independent. And as they are independent, so the product of A and B is often interpreted as the indirect effect. So there's a problem here because this assumption is based on a very strong behavioral assumption. The assumption states that, while there's no heterogeneity across individuals in how they would respond to the curriculum if they are assigned to adopt a new curriculum, right? And also how instruction may affect student learning could differ across teachers, across students, across school settings as well. So in our case study, this behavioral assumption may not hold, for example, if teachers who are more ready to use a new curriculum, therefore they are more responsive to the treatment and they were ready to transfer them an instruction to implement the new curriculum. Such are the teachers who would have a higher value of A, right? The more responsive teachers would have a higher value of A. They could also be the same teachers who believe that transformed instruction will produce a greater benefit for student learning, right? And for those teachers, their belief could be turned into practice. And those are teachers who would likely have a higher value B as well. So it's a likely scenario in which A and B will be positively associated. And that's very important because such a heterogeneity is an important part of the reality that we shouldn't ignore. And when in fact A and B are not independent, the conventional methods will give you biased results of the indirect effect as well as the direct effect. So, whenever we use a method, we have to be acutely aware of the assumptions and how important those assumptions are and how plausible those assumptions are on scientific grounds. I think that's my last question. Should the mediator, I'm sorry, I clicked the wrong button. Oh yeah, that's right, yeah. So this question is, should the mediated outcome relationship be constant? This is asking whether the mediated outcome relationship may depend on which treatment condition you are in. So it's conventional to assume that mediated outcome relationship will be the same under the treated condition as under the control condition. But this could also be challenged on theoretical ground. So for example, Judd and Kenny mentioned, they pointed out in the 1980 article that for the mediation process to work, the treatment may not only change the value of the mediator, but also change the mediated outcome relationship. Extremely important point that tends to be overlooked in the later decades. So in this case, we could think of the new curriculum that may not only raise the quality of instruction, but may also enhance the impact of instruction on learning. So under the current curriculum, when teachers use more scientific inquiry instruction, we expect it will have a positive impact on student learning. That positive relationship is there under the control condition. But with the new curriculum, if teachers transform their instruction to use more inquiry-based discoveries, it could likely have a much larger impact on student learning. So under the new curriculum, the positive relationship between instruction and learning could be much enhanced, right? This is the case in which the mediated outcome relationship could be different across the treated condition and the control condition. And that's very important. So there are quite a few recent methodological developments that allow for such non-constant mediated outcome relationship, allows for treatment by mediated interaction. Therefore, overcomes these constraints. So it's important to remove some of the unrealistic assumptions, right? Because unrealistic assumptions, whenever you make an assumption that doesn't hold, you pay a price because the price is you have biased result. So lastly, I just want to mention that we are looking at educational interventions carried out across school organizations. And this is the picture you have seen earlier. And my research team has focused much of our attention on multi-sided causal mediation analysis, which is really fascinating because we are saying, if there's a replication of the same study across all the schools, right? In each school, you have a treated group and a control group, and say that they were randomized to start with. And there will be, you could study the causal mediation process within each school, but moreover, you could see whether the process may vary across all the schools. Well, to start with, we started with total effect. The total effect of curriculum on learning might not be the same across all the schools for a number of reasons. Howard Bloom gave a talk a few years ago at Street annual conference. He pointed out the 3 C's, as I remember. The first is, these sites may differ in the composition of students and teachers, right? So if the treatment impact depends on who you serve and who delivers the instruction, composition matters. That could explain heterogeneity across these sites. The second, context matters. Here we're talking about organizational context or community context, right? For example, how strong, how effective is the principal leadership? That could have an impact on the total effect. And then lastly, contrast matters. How much is the difference between the new curriculum and the current curriculum, right? So that's the third aspect. And the same idea would apply to color mediation analysis. The mediation process may depend on which population the school is serving. It may depend on how strong is the principal leadership. And it may depend on what type of instruction the teachers were already using before they adopt the new curriculum, right? How large is the discrepancy between their past instruction and the instruction that is specified by the new curriculum. So all those could cause a variation in the mediation process across all the schools. So multi-site color mediation analysis is trying to quantify between-site variation in direct effect and indirect effect. So unpack, each of those black boxes and then see how they differ across settings. So we have, our research team has a number of articles coming out in just the past couple of years. And the most recent one was published in JPAM, in which we look at not just one mediator, but the two concurrent mediators. As in theory, there could be multiple pathways through which the treatment can affect the outcome. So lastly, I just want to draw your attention to my 2015 book, Causality in a Social World, Moderation, Mediation, and Spillover, in which I tried to provide a comprehensive introduction to these very important topics and I used extensively examples from education and public policy to reveal the latest developments in the methodology on these topics. So I will end here and I'm ready for questions.
Great, thank you so much. In the interest of time, why don't we, there's one question to come up here before we take our break. Can you speak a bit more about using weights versus using the pool mean differences? And when and why,
Sure.
and what the advantages are?
Well, one important difference is when you pool mean difference, depending on how you use that, right? I don't know if you want me to talk about it in the context of causal mediation analysis or in the general causal inference setting, in which you only look at the treatment effect on the outcome. And for one thing, weighting is very, very flexible because you could have more than 2 treatment arms, and the treatment can have multiple categories. Weighting is very accommodating. It's unconstrained. While when you pool mean differences, there's a question about how you conduct a global test if you have multiple treatment arms. But weighting is easy to use to just sort of like approximate a one-way ANOVA analysis framework everybody has trained in experimental design. So the intuitive idea of the weighting is you just transform these groups to approximate the kind of randomized experiment you would like to have. And you don't have to specify an outcome model, because I think I mentioned that whenever you specify outcome model, you find a confounder, you put it in your regression model, but your functional form was wrong. If the functional form should be nonlinear and you misspecify the linear, you would fail to remove the bias. So that is a major downside, and the weighting would avoid that. So weighting is, especially if you use a non-parametric approach to weighting, it has certain important strengths. But I'm not saying putting conditional mean difference is inferior. It has important strength and it has a lot of flexibility as well, especially when it's used non-parametrically, such as you can use matching or stratification, or people may specify a non-parametric model. So to avoid, misspecifying the outcome model. So both will have a lot of flexibility, and it would be good to see how they converge, the results converge.
Great, thanks. Well, we're going to take a quick break here, pause for a few minutes. There'll be a moment at the end of the course too. There'll be time for some general questions. So we're going to take a 5-minute break, and when we come back, then Professor Raudenbush will be up then. So we'll see you in 5 minutes.
Partial thickness undersurface tearing of anterior fibers of the lateral facet. Pure attenuation of posterior superior fibers.
Review script.
With a tiny partial
Finds
thickness tear
cubic benign involuted fibroxanthoma,
at the
thin the
apex of the
posterior
radius
lateral distal
period.
metaphysis.
Okay, our break is about wrapping up here. We're going to turn to Professor Steve Raudenbush.
Steve, you're muted.
Steve, yes.
Yeah, that was a disaster. Yeah, again, for me, thanks to George Wimberly and the AERA for this wonderful opportunity to learn from my colleagues. It's a great opportunity. I want to talk about STEM curricular interventions, as we all are. I want to talk about multi-level theory and methods, and my comments. Can you hear me, by the way? Okay. Comments are based on this article in the Annual Review of Statistics on educational experiments with my colleague Dan Schwartz. So I'm sure you've all heard the assertion that the randomized clinical trial is the gold standard for causal inference. There's a lot of truth in that. The iconic case is the drug trial. Individual patients come into the clinic and are randomly assigned to get a new drug versus a placebo. After some time, we take the average outcome of those getting the new drug and we subtract the average outcome of those getting the placebo. And that mean difference in our sample is an unbiased estimate of the mean difference in the population our sample represents, for all the reasons my colleagues have mentioned. What are we really assuming, though, when we have this iconic experiment? Well, one thing we're assuming is there are no peer effects. We're assuming that the treatment assignment of one person doesn't affect the outcome, potential outcome, of the other person. And so that means that, for example, my treatment assignment, let's say if I'm assigned to the control group, my outcome won't depend on whether somebody else gets the treatment, okay? We can kind of see in COVID that's not exactly necessarily going to be the case. But imagine that one of the participants is my wife, who's getting, I'm not getting we're both depressed, I'm not getting the drug, but she is. But if she's getting it, it could actually improve my mental health, right? We don't think about that necessarily in the drug trial. The other thing we assume is that the version of the treatment that everyone gets is the same. It's the same drug. It has the same chemical composition, right? But perhaps the physician who prescribes the drug, perhaps they vary in their effectiveness in encouraging people to follow the drug and to take it correctly. There would then be physician effects. I want to mention my colleague, Doug Steger, economist at Dartmouth, who studied surgeons and teachers. And Doug has a very compelling case that surgeons, and this is scary if you're going to face surgery, surgeons vary in their skill as much or more than teachers do. Doug has pictures of the hands of the surgeon and how fluent they are and how automatically they do the right thing. So when we go to education, we look at education, we don't really think there are no peer effects. We really think there are different versions of the intervention simply because they're different teachers implementing it. And so we're much more attuned to the social environment. And it may be because in education, these peer effects and these agents, these effects of heterogeneous agents, not the physicians, but the teachers, that these things are maybe are non-ignorable, okay? And so we ask ourselves, how do we take these things into account? How does knowing about these things change the design of our research? So one question that we ask that hasn't been as often asked in medicine is, what should be the unit of intervention? Oops, I don't want to, there we go. Does the intervention, so in a school setting, does it require school-wide collaboration? And if so, perhaps the school should be the unit of assignment, which is not usually what we do in drug trials. We usually make the person the unit of randomization. I want to give a couple of examples where it looks like the person is the unit of assignment, but we got to be careful because of peer effects and different versions of the treatment. One is Algebra for All, Chicago, 1997. Takako Nomi has a nice article on this. In 1997, the Chicago Public Schools required every student to take algebra in 9th grade. Prior to that, there were schools in which some students took algebra and some didn't. There were other schools in which everyone took algebra. At a superficial level, it looks like the unit of assignment is the child. The child in a particular school who would not have taken algebra in 1996, if they were in 1997 in that school, they would take algebra. And under the standard assumptions of the drug trial, the child who would always take algebra, no matter even before or after the policy, would never have an effect of this policy. Well, what Takako Nomi showed was that when the schools implemented Algebra for All, they completely reorganized the scheduling of the classes. And classes became far more heterogeneous in skill. Kids who wouldn't have taken algebra in the past were now in algebra classes with other kids who had higher prior levels of achievement. And Nomi shows convincingly two things. One is the kids who wouldn't have taken algebra did not benefit from the treatment, and the kids who would always take algebra, they actually they suffered. It turns out the quality of instruction went down when the class became so heterogeneous with so many unskilled kids. So actually, there was a treatment effect on those whose treatment value taking algebra never would change because other people's treatment assignment changed. Following 97, Chicago realized this wasn't a very good policy, and they enacted a policy that turned out to be far more effective. They doubled the instructional time of kids in algebra who were below a certain cut point. Nevertheless, and so that makes it, that's called a regression discontinuity design. It's one of our favorite quasi-experimental designs. If we can't do random assignment, we like the regression discontinuity. We look at kids who are just above or below the cut point, we compare them. And there's some amazing effects of this. We have, my colleagues and I, including Takako Nomi, have a new paper coming out where we show that kids who had double dose algebra in 03 in 9th grade had higher graduation rates in college as a result. However, it depended tremendously on how the classes were organized. In schools that reintroduced tracking in such a way that those kids in the median, at the median who were scoring just below the cut point, if they were attending classrooms with very low skilled kids, the intervention had no effect. So the same point holds, that the entire school was changed in fundamental ways by an intervention that on the surface was strictly an individual level intervention. And two of the favorite statistical techniques in econometrics, in the Algebra for All, it's the DID, the difference in difference technique. In the double dose algebra, it's the instrumental variable technique, which are designed for individual level assignment actually broke down, and we need a broader class of statistical models because there's actually assignment happening at 2 levels. If school policy is changing, that's at level, we call it level 2, the school level. And within the school, the actual class assignment of the kids is changing. And so we have actually a multi-level treatment situation going on where there's a treatment at 2 levels simultaneously occurring. So one of the things I'm very interested in is then how do we then statistically accommodate this very common kind of situation? Well, maybe the intervention affects the whole class, but without school-wide collaboration. So the classroom could then be the unit of assignment. Carol Connor and Fred Morrison, the late Carol Connor, who tragically died this last year, ran a number of really, really interesting trials where teachers would assess children and then tailor the instruction to the different skill levels of the child, reassess, reassign, and retailor the instruction. My colleagues and I have something similar for preschool kids in math. The reason that we could have perhaps school classroom level random assignment is that you might say, well, what about the control classrooms, the people who don't have this wonderful system? Wouldn't they also be affected by the intervention? Well, not necessarily, because if you don't have the assessments, you don't have the tools, and you don't have the practices that go with the tools, it's kind of hard to have happen in another class. So the classroom makes a good, there's still a possibility of spillover between classrooms within schools, but the classroom seems a sensible unit of assignment. What about the child as a unit of assignment? We see this increasingly in technological studies. Kids are assigned at random to online interventions, and they log on and they work with a certain computer program or versus another program or versus not having the program. And it sounds like it's just individual level, it's independent. But we know actually that even when kids are working online, even under COVID, they're working in a social environment, and how they are motivated and how they process what they're learning from the machine still depends on social interaction. So this could still be a problem. So let's just talk a little bit more about the level at which we assign individuals to treatments. If we can assign the individual to a treatment, we get a big gain in statistical power. Moreover, if this is done in multiple schools, in each school we have an experiment. I think Ken alluded to this. So there's a replication of the intervention across multiple school settings. It's a fleet of randomized studies, and we like replication. We can see heterogeneity. We can see if there's heterogeneous treatment effects under different circumstances. The problem with individual assignment within schools, even when it's machines that are doing the treatment, it seems, is that the experimenter has an incentive, and this is in my view at least, to change the nature of the social interaction. There's an incentive to reduce social interaction. I don't want you talking, Johnny, I don't want you talking to Susie because Susie's in a different treatment group. That's probably not the way we want to optimize learning. It certainly, John Dewey would not be pleased. So a very common design is this, and Ken mentioned this as well, is that within each school we'll assign the classrooms at random. And if you can do it, if you have the kind of intervention that Carol Connor had, you can do it. You can gain statistical power because classrooms are numerous. If you have a study of 30 schools, you could easily have 100 to 120 or 150 classrooms. You get adequate power. There's a treatment effect in each school, so we can actually look at the generalizability of the treatment effect across multiple settings for different kinds of kids. That helps us with generalization. But there still could be an incentive to minimize the interaction between teachers. That is an incentive on the part of the researchers. I don't want you, teacher A, to talk to teacher B, who's in a different treatment group. I don't want you to share ideas. So we have to think about the possible spillovers. Generally, in education, we usually think the spillovers are a good thing. These are things we actually want to promote rather than things that we want to prevent. So the other kind of design is we assign the entire school to the experimental or the control group. The school randomized trial. It tends to be expensive. Howard Bloom and I and Jessica Spybrook have done a lot of work over the years looking at the statistical power for these all of these different designs, and we have software that you can use. I can show you where to find it. It's very simple and easy to use. We have papers on this. You need to have generally quite a large number of schools to get adequate power, something in the neighborhood of 50 to 60 or more schools to have a school randomized trial that's really going to work for you to have enough power given the typical effect sizes we see. We can improve power by using school level covariates. But there is still this problem that they tend to be expensive. You can't estimate the treatment effect in each school because each school has one treatment or the other. But the school is often the natural unit of intervention. In fact, the interventions, many of the curricular interventions in STEM and in reading and other areas are intrinsically school-wide. I mentioned the building blocks of Doug Clements and his colleagues for preschools. The entire school adopts the curriculum. That's how it works. So the other kind of assignment we're seeing more and more of is the whole school is the intervention. So we see this in the Head Start Impact Study. We see this in charter school experiments. In the Head Start Impact Study, people in a local area, there's more eligible people for Head Start than there are places. We advertise for applicants. There are more applicants than there are places. There's a randomized lottery. And the winners of that lottery are then in the experimental group. They're assigned to go to Head Start, or and the Head Start has a certain math curriculum, right? Or they're assigned to a school that has a certain math curriculum. And that's a wonderful study for getting the causal effects of entire schools. And it has the advantages of individual assignment, including the power. And you get an effect for each and every school. So you have the fleet of randomized trials. But the problem, of course, is that the curriculum is confounded with other school attributes. A school is not just a STEM curriculum. It's got a lot of other stuff going on that's having effects. So here's another question that we've really gotten kind of fixated on. And that is, what is the target of your generalization? And this question exists regardless of what the unit of either random or non-random assignment is. So whatever the unit of assignment is, whether it's the individual, the classroom, or the school, you can set a different target for your generalization. You could think of a population of eligible children. If this curriculum were generalized, what would be the average gain across the population of kids in 9th grade or in some set of kids? That's usually one question we want to ask. But if an intervention really requires the change in teacher skill and knowledge, the ability to use assessments, it's a professionalizing kind of intervention. The teachers are the key unit. Maybe we want to generalize to a population of teachers. Or if it's a school-wide, actually, in any case, we might want to know, we'd have a distribution of treatment effects on each school. We'd not want to know what is the mean and variance of that distribution. And we might then ask which kinds of schools benefit. So we have, with children, teachers, and schools, 3 different populations. And because classrooms have different sizes and schools have different sizes, the answers to those questions can be quite different unless the treatment effect is constant, which is, by the way, what is assumed still in most curricula on causal inference and regression and experimentation, is the assumption that treatment effects are constant. Believe it or not, it's a very strong assumption. So the question then arises, when are treatment effects constant in education? And if you look at Michael Weiss and his colleagues, the answer is when the effect is 0. When there's a completely inefficacious intervention, nobody gains and nobody loses. Well, people could lose, but the effect is 0. And what Weiss and company showed in their article, I've got some references at the end in this. We're going to distribute these, and you can see these references. Pretty much whenever we see an on-average treatment effect in a large randomized trial in which there is an effect, it's typically heterogeneous. Settings vary, people vary, and the effects are heterogeneous. And therefore, we have to worry about which population we're targeting. And we really do have to worry about the heterogeneity. Under what conditions does this really work? So I want to say that the modal experiment, by the way, since 2002, there have been many hundreds, 300 or 400 randomized trials, large scale, funded by the Institute for Education Sciences. Prior to 2002, there were very, very few experiments in education in the United States. So you might ask, well, what is the most typical research design in these experiments? And if you look at Jessica Spybrook's work, you'll see it's the multi-site cluster randomized trial. And here's what I mean by that. We've got level 1 are the children. This is my HLM talk. The lowest level units are the kids at the least aggregate level. They're nested within classrooms, and the classrooms are assigned at random within schools. So it's a multi-site trial because it's a trial that occurs in each and every school. Randomization is by cluster, i.e. by classroom. That's one example of a multi-site cluster randomized trial. The other kind is we've got the kids again nested in schools, and the whole school is assigned at random, but this occurs within many districts. So we get a different treatment effect for every district, and that's the site. And a lot of questions have come up about how to best design these studies. How many units do you have to have at each level? And we have a lot of tools now for answering those questions. But also, how should you analyze the data? So let's just consider the kind of modal design where the kids are within classrooms, the classrooms are assigned at random to the intervention within schools. Well, for me, that's just a no-brainer. It's a 3-level hierarchical linear model. Level 1 are kids, level 2 are classrooms, level 3 are schools. We have an equation for each level. The treatment effect is a level 2 variable. It's a classroom level variable, and its effect randomly varies over schools. It's all very straightforward. The economists have not preferred this design mostly. I mean, more and more people are picking it up, but a lot of people don't. They don't like the idea of a random intercept at the highest level, that is at the school level. They prefer to use fixed effects. And the reason for that is fixed effects absorb all between school variation and therefore eliminate confounding. Unobservable differences between schools cannot be correlated with treatment assignment. And this is true in a randomized or a non-randomized trial. I always have been saying, well, we can solve this in HLM with centering. No, I'll show you how to do it. I got a paper on it. But one way to reframe this is, and the problem, I should say, the problem with the fixed effects model is it ignores the clustering. In this case, it ignores the nesting of children within classrooms. And by the way, it assumes a constant treatment effect. And this is a big problem. If you read our article, you'll see why. So Howard Bloom and I and Mike Weiss came up with a hybrid model, which doesn't require fancy centering or whatever. Fixed school intercepts, but a randomly varying treatment effect for each school. And then in addition, teacher random effects within schools. It solves the problem the economists are worried about very simply. No dummy variables are needed. There's no centering. It's really, really computationally just very efficient. And we have a paper on that. And we show how this can be a very robust way to sort of put together the advantages of the hierarchical linear model with the criticism from economics of needing to have the fixed effects. I should mention another analytic issue that's coming up a lot is imbalanced data and missing data. We're getting into, we want to estimate the average treatment effect, the variance of the treatment effects, and we'd like to know whether there's a correlation between the control group mean and the impact. And if the control group mean is high, do we have a high impact? That would be an equalizing intervention. And for these purposes, we're developing multi-level weighting and imputation models. I think, how am I doing for time? Are we running? I think we're running a little behind. Let me see if I can get through this quickly. I'll just say that non-compliance, which has been studied enormously in the last 15 years in various randomized trials where some people don't participate. We use treatment assignment, random treatment assignment as an instrumental variable. In a multi-site trial, every site has a specific subset of people who are the compliers. They can be quite different from site to site. So we have to think about how to take into account that kind of heterogeneity. And that actually just reveals, that replication reveals a big problem with the standard methods for non-compliance. We need to fix those a little bit. And multi-site mediation, and Guanglei has done so much to talk about the mediation. I'm not gonna say anything in detail beyond what she said, but I do want to at least make the point that when the school is assigned to the intervention, we have level 3 of the school is the unit of assignment, but the teachers comply or don't comply, or the teachers transform their instruction or don't. Now there's a treatment level at level 2, at the level of the teacher, and the kids are actually being non-randomly assigned to classrooms where the instruction is differed within each treatment level, which is being randomly assigned at the school level. We have this multi-level design that we have to cope with. I won't say too much more about how we handle that, but that's a topic of research now. Okay, so the summary is choose the level of random assignment, or if it's non-random, you still have to think about what is the level of assignment. And if you don't have random assignment, I strongly recommend sketch the randomized study you are approximating with your non-randomized study, and to get the design right, to get the theory right, the generalization right. And then think about the techniques my colleagues have mentioned about pooling, conditional differences, weighting, et cetera, in order to approximate that randomized trial. Take care to capitalize on heterogeneity. Multi-site trials generate heterogeneity, and that's a good thing. Heterogeneity is what we live off if we're researchers. We want to study it. We want to understand it. When does this thing, why, and for whom? Tremendous opportunities here. Clarify your target of generalization. Let the analysis method flow from the design and the target of intervention. So I've got some references here. When you get these, you'll see some of these studies I'm referring to. So thank you very much.
Thank you so much. Just in interest of time, one point, can you talk a little bit more about how randomized block designs are in terms of treatment effects?
Well, yeah, so when I say a multi-site randomized trial, really, it could be called a randomized block design. The site is the block. So literally, if it's the school, and within the school, there's intervention, there's assignment of classrooms to treatment and control, then that's a randomized block design where each block is the school. It's a natural, but they tend to be natural administrative units in education. Now you can go further and you can match the classrooms within a school. We did that in the study that I referred to with the little kids with math. You match the classrooms, and then within those matched pairs, or those typically pairs, or those blocks within the school. So you have actually a matching and a random assignment with matching within the school. And this can give you more power and a better balance on some key observables. So whereas the school itself is a block, you can have literally within that school, you can match those classrooms. Or if you're going to assign kids, you can match the kids and then assign them to random. You're getting more power, and you're getting a better balance than you would have without blocking. And this goes back, way back to agricultural research, 75, 80 years. We know that.
Great, great, thank you. Well, I want to say that we will have some questions at the very end in the post discussion, but in the interest of time, I want to turn back to Ken Frank, who's going to talk about social network analysis. Thank you, Steve. Ken?
Thanks, Steve. I think you'll see that a lot of things that Steve was just saying set me up well, not an accident. He and Tony Bright have had huge influences on me. And so I'll pick up maybe where he left off or go in a little bit deeper. And I do want to say, I'll try to be about 15, 20 minutes. I hope you'll stick around. Kaitlin, Torphy Kanaki will be doing stuff on social media after me, and that will play very directly off of what I'm going to do. So what I'm going to say is going to be based on a couple of fairly recent overview pieces that I've given reference for here. Most of the comments I'll make, a basis for them can be found in those two pieces. So if we go back to our overview, so sort of our anchoring picture, we had the curriculum and professional development, and here's the teacher implementing, and we have some outcome. And what I want to highlight, and Steve was really already pointing to it, is that the teacher is living in a network world. The teacher could be talking to other teachers within her school, and I think later on Kaitlin will talk about how they're talking with others outside their school. So the teacher has this network, and the students also have a network, which might even become more active in a high school setting. And really the classroom can be thought of as a place where these two networks confront each other. And with very complex dynamics. So, and then when we think about the curriculum and the professional development and how they could affect things, given those dynamics, it gets a little more complicated, but we can start to take some pieces apart. That's what I'm going to try and take you into. So a little bit of a basic definitional stuff. What is a social network? So for me, it's a set of actors in the ties, which are resource flows or relations, stable states among them. So an example would be close colleagues among teachers. Close colleagues is a relationship, it's stable among teachers, or the help, the tie that one teacher provides another. We could also have friendships between adolescents. Those are stable or changing depending on your view of adolescence. And we could have communication between actors in different organizations. It's more than social media, but it includes social media. For me, actors have to have agency. They have to be able to take deliberate action. So I'm okay thinking about a school as an actor. In some contexts, I'm okay. I think it's important to think about teachers and students as actors. But I do have one project where we think about organizational routines as actors, and that's a little bit more of a challenge for me sometimes. One of the questions I always get asked is, how do you collect network data? How do you get that? And the answer is, we ask people who you talk to. So this is an example on a survey, and it's an actual survey that was used. We ask somebody to put in their name, this is Lisa Jones, and to indicate who helps you with technology at your school and the frequency with which you interact with each person. And Lisa Jones listed Bob Jones here. So person one is Lisa Jones, Bob Jones is person two, and they talked at a level of 2. So this we get coded as a 1, 2, 2, and then we can use this type of data in our analysis. You could adapt this kind of instrument to the new curriculum. Please indicate who helped you with the new curriculum and the frequency with which you interacted with that person. So this is kind of for a general diffusion of innovation kind of question. I also like to ask people, who are your closest colleagues in this school? And it comes from an instrument like this. Whenever we ask about social network questions, one of the mistakes I've made several times and has been made on many studies is we don't spend enough time asking about the key behaviors or beliefs that could be responsive to a network. So if we're asking teachers about their behaviors and beliefs, we might use a survey instrument like this, where we ask the teacher to fill in the blank. I use computers to help me, with a scale of never to daily, introduce new material into the curriculum, guide student communication. These are the core things that a teacher tries to do every day. We adapted these from some other instruments. And then we ask, how much do you use the innovation to help you with those daily practices? Notice that we did not ask, how much do you use computers? Or how many students do you use computers with? We tried to get inside the teacher's mind and ask and think about the things they're trying to accomplish, and are they using the innovation to accomplish that? And again, this could be adapted to, I use the new curriculum to do the following things. You'd have to adapt it a little bit. So now we're armed with a measure of a network and a measure of a key behavior that might relate to the network. And this goes to some of Yanyan's measurement principles. We worked pretty hard to make sure this was one-dimensional. And we did explore IRT measures of this measure. You can read about it down here. Now we can get fancy. We can draw we can create a visualization of the network. And so in this particular picture, each dot represents a teacher, and lines between the teachers indicate who's close colleagues with whom. The thickness of the line indicates the frequency of the interaction. The coloring was identified by my community detection algorithm. It's called ClickFinder. And so the idea is it tries to identify a concentration of close collegial ties within the groups and sparse ties between the groups. The shape of the nodes represents what grade they teach. Circles are grade 2, squares are grade 3, and they call it a thing as mixed grades. This is important to recognize because the grade 2 teachers have this wonderful cohesive network. That's great, but there aren't very many connections between grade 2 and grade 3. And imagine yourself as an 8-year-old transitioning from grade 2 to grade 3, and your grade 3 teacher teaches very differently than your grade 2 teacher, doesn't talk too much to your grade 2 teacher. That could be a challenge. And actually, Steve and Guanglei have written about the transition multiple treatments between grades like that. It can be a real challenge. So there's a little link there if you want to get some code for how to kind of run this stuff in R. It's still a little under development, but it works. Might have to hack at it a little bit. Now, given this structure, we can think about the diffusion of innovations. This structure was shown based on close colleagues. That's the lines between teachers. Now I've erased the lines and instead put in new lines about who helps whom use technology. And I've made the dots represent the level of technology use at time 1. So this teacher here has a lot of knowledge about how to use technology in her classroom. So does this teacher. And one thing you can see is that there's a lot of expertise here that, and there's not much conversation between the folks here and here, and these people have kind of smaller nodes. So this is a challenge for the school. If we want all the teachers to use technology, the technology is very isolated in this school. So what are we going to do about this? Well, Teacher 20 kind of figures it out. And I interviewed the teachers in the school. I observed them in their classrooms. She figured this out and she went and talked to Teacher 2. And then she went and talked to these other teachers. And when she did, she created big changes in the practices as evidenced by these ripples, which indicate increase in use of technology between time 1 and time 2. And she triggered big changes down here. This teacher was able to trigger changes within her own group, but this teacher was key to the diffusion of the knowledge needed to support implementing computers throughout the whole school. So when Steve was talking and when Guanglei was talking about the role of the teacher and teacher spillover effects and thinking about the school as an organization, this gives us a chance to study it. And not all schools pull this off. Sometimes there's no Teacher 20 and the knowledge becomes isolated. The supported knowledge becomes isolated within a particular group. And then it becomes very difficult for the others to adopt the innovation. That can create some very complex dynamics in the school, potentially polarizing the school between the haves in terms of knowledge support and the have-nots. In this case, Teacher 20, a bridging teacher, which is really key to diffusion of innovations, figured it out and pulled it off. Let me show you another teacher, another picture, slightly different style. So this is transcript data, high school transcripts. Each dot represents a student. Each square represents a course that they took. Lines between dots and squares indicates a course taken by a student. There are groups of students who take courses together. Now imagine you've implemented a new curriculum in the school. That could create a new set of courses such as over here with genetics and analysis, just as one example. That allows this group to form around those courses. If those courses did not exist, the social structure of the school might be different. These individuals might take courses with people in other groups and therefore associate with people in other groups more often. So just by introducing these courses are opportunities for interaction, they're venues. And as such, you're changing the social organization of the students in the school with a new curriculum, or you have the potential to. Okay, let's talk a little about two processes in the school, but I'm going to focus on influence. When we talk about influence in a network context, we talk about changes in actors' beliefs or behaviors as a result of exposure through interaction with others. So a teacher changes her use of computers as a result of the use of closest colleagues, or student changes motivation as a result of motivation of course mates. We've been talking about motivation in the chat. I followed a lot of people bring that up. So to study this, to actually include it in a model, what we do is we make a network exposure term. So we take the help that A received from B, C, and D, and we multiply that by the attributes of the people providing the help. I want to highlight something here. This guy down here is not so helpful. So it's not just how many people did you talk to, it's what can these people provide to you. And it looks like these two folks could be pretty helpful and this guy not so much. And so when we get data to study networks, we don't just get data on the network, we need to find out attributes of the people in your network optimally. And how much do they know? How helpful are they? Then we can make a term out of this. We can take the mean or the sum of all the help that you can get, and then we can start to use that in a model to predict your new behavior. Now there is something lurking here. Not only could these people influence you, but you have chosen to talk to each of them. So there's something called selection in network analysis, and it's how you select with whom to interact. And you might say, well, I don't want to talk to this guy because he's not so helpful. Or, I really want to talk to her because I have something in common with her. So people choose their network members, and then they can be influenced by them. And so we're always worried about the two processes going on because humans have agency, especially in schools. If we are to model the effect of exposure to others, which is this term right here, on a teacher's outcome behavior, this would be the exposure effect, and we would call that influence. But we're worried about selection. We're worried that we might have selected to interact with somebody based on prior behaviors or beliefs. So an example here is, let's say we're modeling implementation of an innovation. I started with a fairly high level of implementation. I talked to people with high levels of implementation. Later on, I have high levels of implementation. Is that because I talked to them? Well, it might be because the selection effect dominated. It wasn't that I was influenced, it's just that I had previously had a predisposition or an inclination, and that's what made me talk to them. So what can we do about this? Well, for starters, we should use prior behavior. We should control for my own prior behavior. In almost any scientific enterprise, when there's an alternative explanation, a good thing to do is get data on it and account for it in your models. And so this is an example where we should do that. And then I also emphasize that we're looking at the effect of prior behavior of network members on a teacher's outcome behavior. It gets very tricky if you try and do this contemporaneously. You'll almost always be exposed to bias. So we're really going to leverage longitudinal data here. And the behavior here might be curricular implementation or use of technology, any innovation that we want to diffuse. So now I'm just going to show you the latest and greatest. Yeah, we control for prior behaviors. We're careful about using the prior behaviors of network members as a predictor. Even so, there might be other things that we need to control for. So what can we do about that? And there are these new techniques called latent space techniques. And what they do is they leverage the network data and the visualization. The location in a picture in the visualization tells you something about people's preferences that we can control for. So if we go back to this picture here, the latent space is this is the whole latent space. We can think about how far apart two actors are plotted. And let me just take that, narrow it down a little bit. And this will be the latest and greatest and last big thing I want to show you. So here we are in this latent space, and A and B are plotted close together. Well, it's partly because they talk to each other, okay? but it's also because they have actor C in common. They both are tied to actor C. And so that's telling us something. Why did they both choose to talk to actor C? Well, there might be some omitted variable, something unobserved about A and something unobserved about B. And C shares that. And that's what made them all want to talk to each other. Maybe they all like talking about baseball or something like that. Or maybe they all have the same predisposition to adopting the new curriculum, even though we didn't measure that directly. But the fact that they're plotted together tells us that they're likely to have shared that predisposition. In fact, if they were plotted further apart, like in this picture, it's because they both don't talk to C. So that distance in the plot, in the picture, tells us something about some things that we cannot observe about A and B other than through the fact of their attraction to C, their mutual attraction to C. And this theory actually goes back to Theodore Newcomb and Heider, ancient stuff where they used the people in the network to indicate the preferences, unobserved preferences of people. So what we do now is we control for distances in our models. We control for plotted distances, and that through simulation, we can show that that seems to account for some of the omitted variables that we would have liked to have directly controlled for. Of course, it'll never be perfect. And so we can't control for everything. And a lot has been coming up in the chat about that. How's the assumption of no omitted confounder like Alexander Hamilton? They will never be satisfied. It's just almost an unwinnable, if you're looking for proof that we've controlled for everything, you might not get it. But what we can do is do our sensitivity analysis and talk about, well, where there's strong evidence, how much bias would there have to be to change your inference? And I will note, I put in the chat, people tried this link earlier. It's working, it just got overwhelmed. $100 later, which I'm happy to pay, the thing's back up and able to tolerate a lot more hits. I'll pause there. I'll stop there.
Thank you, Ken. That's great. One question that came up here in an interesting time, I'll keep things short and we can move on to Kaitlin. But can you say something about sample size? What are adequate sample sizes for social network analysis?
Yeah, so there's two pieces. If you are trying to model a teacher's behavior, how much she adopted an innovation or her practices or a student's behavior, then we're going to get you into a regression framework or a standard modeling framework, maybe multi-levels, almost certainly. And the rules that apply in those models apply here. You're at an individual or a teacher or even, yeah, probably an individual level. So that's part one. Part two is if you're modeling selection, you have as many observations as you have pairs of people or dyads. So actually the degrees of freedom go up. You know, for 10 people, you would have roughly 90 cases. And then we're into more or less standard modeling practices, although they're a little tricky. But we get a lot of degrees of freedom at that level.
And also there's a question about the source of the data. Can this be from one's own observation, from video data, or from classroom interaction data?
Yep. You can code this off a video of classroom interaction. I have a colleague, Carrie Rosseth, who has done exactly that. You can get it from email communications, electronically. We do a lot digitally. And in fact, Kaitlin's going to talk about how you can get data like this off of something like Pinterest, social media.
Well, great. Well, thank you. I think that's a good segue into Kaitlin's presentation.
Okay.
Hello. I will share my screen. Hi all. So today I'm going to be talking more about the computational methods related to education science. And if you're interested in learning more about computational methods and how we apply it within our work, you can check us out at teachersandsocialmedia.com. So going back to the original theoretical model for curricular innovation, what I wanted to point out here is that we can think about teachers' practices and students' engagement as it relates to all of these other factors, including the curriculum, the type of professional development that teachers engage within, the social networks which they hold within their schools, their districts, or other professional affiliations, and how all of those things relate to student learning. However, we also know that individuals within our world, and for sure now with COVID-19, are more engaging within online space than ever before. And so you can see here that there's this network of connected individuals within social media space behind all of these things that we're seeing within teachers' other work life practices. When we think about computational methods, it's one way to get at research questions that one could answer. So you could say, okay, how is this teacher, and this teacher happens to be me in this picture, planning for her instruction? So we can go into teachers' classrooms and we can observe them. We can survey them and ask them questions on a survey, or we could interview them. These are all ways that we can get to that answer. However, the challenges to those approaches are scale. For example, if we want to do that with one teacher or even a handful of teachers, that's very achievable. With getting into the hundreds or even potentially the thousands or hundreds of thousands, that is much more challenging to scale. And then in addition, for particularly interviews, survey instruments, or even observational instruments, how reliable are those instruments? How representative are those instruments of what we're actually trying to answer? And are the questions that we're asking valid or authentic? And are they soliciting a response from a teacher that teachers think they should be answering, or is it an authentic response? So another approach, thinking outside of the physical space we live within, but moving on to the virtual space, is we can look into individuals' online engagement. And some of the benefits to this approach is that those engagements are authentic, meaning that individuals are choosing to engage with them, not necessarily anticipating what people might be thinking if they were observing. They happen within real time, and they allow us to see, in this case within education, how individual teachers are curating their resources. So going back to the question, how is this teacher planning for her instruction? We can see an example here of all of these different resources within Pinterest as examples of what she may be choosing. So the curation teachers choose to engage within to support their instruction impacts their students that they are working with, but then their students' needs hopefully are relating to the types of instruction that teachers are curating. And here, this Roll and Solve Math Facts is an example of one resource that I picked up off of Pinterest. So a teacher might curate this particular resource to her board, and she can save that as one of her teaching ideas, which then links to her social network within online space. And those people may also be connected to her within physical space, i.e. her school or district. And we call this network of individuals a socialized knowledge community. So computational social science in education research, like I said, advantages are to observe things at scale, it's authentic in real time, but the challenges are that the observations are unstructured, so they're not designed for education research. Therefore, how you manage the data and put the data together matters when you're making inferences. And that goes again to questions of causality, which we've talked a lot about today. So some responses to that to address those challenges might be to integrate with other data, which I'll show you a little bit about later, such as surveys or interviews or other secondary administrative data like test scores or demographic data from census surveys, etc. But thinking about informational exchange, I want to take you back in time. So in the beginning, informational exchange really happened within 3 estates, which are considered the principal states, including the federal and state, and in the early history, clergy. But with the advent of mass media in about the, I think it was the 1700s, that was, or I'm sorry, with the advent of the Gutenberg press in the 1500s, that was coined the 4th estate. For mass media and information through books and reading. So the exchange of information moved down from just those principal estates to more common individuals. However, with the advent of social media, since Web 2.0, individuals are enabled to connect with one another in networks embedded within social media and challenge traditional hierarchies of influence. So for example, if you were to go out and ask teachers who are in training or in internships about where they seek out information, we have a direct quote here that suggests teachers are not generally turning to textbooks anymore, but they're rather looking at bloggers, or they're looking at social media or their networks of influence online to find support. So we asked teachers who were early in their career, where were they seeking out supplemental curricular resources? And we found that 90% of sampled teachers within a National Science Foundation sample across several Midwestern states were using Pinterest, and 80% of them approximately were using it at least once per month, with at least 50% using it at least once a week. And this also echoes findings from NCSM and the RAND Institute. Teachers are seeking out advice and help within social media, and this may be because they can both like subvert maybe showing a weakness to their in-school peer colleagues, or also just follow mentors that they find to be inspirational online. And that those information flows will go from both people they work within and may be reciprocal, or they may be one way. There's different reasons that teachers engage across different social media platforms. So within Pinterest, the teachers we surveyed particularly used Pinterest to acquire and share resources. However, they may use Twitter more to stay informed or have some type of virtual engagement with one another. So to conceptualize this change and shift in informational flows, we wanted to talk about what this new teacher looked like in schools today. And so the term that we coined for this was teacherpreneur. And a teacherpreneur is a teacher that takes initiative to find and share resources online outside those provided within her local district or her physical collegial network. And this is despite the risks and wasted time and effort and unknown resource quality. And that's what makes it that entrepreneurial spirit. To take it a little further, there's also teachers who are selling their resources within like an educational eBay called Teachers Pay Teachers, which has millions and millions of resources that teachers are engaging and sharing with one another, and has increasingly grown over COVID. So we can think about the educational craftsman as a teacher who is monetizing her resources and sharing them within teacher-to-teacher markets. And this teacherpreneur who might just be looking to supplement her district-provided curriculum within a kind of construct here of a teacherpreneurial guild. So here we have the educational marketplace with the state, and this would be state regulations and curriculum, the traditional teaching profession, and then the more capitalistic markets here. And the teacherpreneur emerges within the space as something that can exert influence across all of these factors and across the profession. So teachers are directly engaging with one another and diffusing information and resources. which is affecting the quality and the profession at large. So we wanted to see, using computational methods, how we could quantify this theoretical emergence that we were conceiving. So we took a sample of 197 elementary teachers, and we identified where they were seeking out their educational resources across what we call online sites. And then we actually downloaded and pulled all of their educational pins from all of those sites, which was 135,086 pins. And what we found is that in general, teachers are turning to teachers for information and advice rather than trusted historically representative like educational entities. So they're turning to one another through teachers' blogs, teachers pay teachers, and those accounted for 75% of teachers' pins, versus only 7% of the pins reflected resources from traditionally educational organizational sites. And those places would include universities, they would include nonprofits, etc. And then when we looked at how many of the pins actually represented educational craftsmen or monetizing resources, we found that within the subsample that we pulled, 72.6% were allowing teachers to purchase an instructional resource through a teacher-to-teacher market. So why might teachers be doing that? Well, basically it hinges on teacher-to-teacher trust. Teachers feeling that they understand one another and the types of challenges that they may encounter within their classrooms. So they choose to seek out information and advice from one another. And that's despite differences in geography, differences in school demographics, different types of professional affiliations. And this echoes what we find within this new conception of principal and mass media, and now what we call the fifth estate, which is the emergence of these embedded networks of individuals. So outside of the informational diffusion within the principal and fourth estates, we see this fifth estate of embedded networks of individuals which are turning to one another within education, and the reasons of their decisions to do this relate to the autonomy that they have to seek out resources and advice, the ability to be more creative and more flexible in their instruction, again, teacher-to-teacher trust, the fact that they trust in the people selling these resources or sharing them are more credible, and that they're able to modify them for their particular students and to support their individual students' learning. And particularly over the past year, with most schools going to at least some types of online instruction, the ability to seek out resources within a fifth estate is being seen even in greater numbers. So I just want to briefly go over how we might build big data applications to create rich data. So for example, we might want to know how the behaviors teachers are engaging in within social media are impacting their students' learning. Or we might want to understand how particular curricular changes are impacting teachers' behaviors. So things we could do are we could identify other various data sources to connect our data to. And in teachers and social media, we're doing just that. So building on US sampling stratification, we collected a nationally representative sample of teachers within Pinterest, and we collected all of their Pinterest education and other data. Then we connected that data to other Common Core and survey data to identify how the types, to be able to answer the types of questions we want to answer. So for example, how are teachers' behaviors affecting students' learning? How are online behaviors changing with relation to the particular schools and districts that these teachers reside within? So these are all the questions that we seek to answer in the future. And how are teachers' networks and the networks they hold within their, well, we know the grade levels they teach within their schools, so we could look at like the type of school-based networks, but we could also look at network changes of influence across virtual space as well. And so you can see here that we have a nested representation of teachers within states and districts and schools and grades. And then we also have a nested nature of data within social media, because there's the Pinterest account of the particular teacher, but then within that, teachers actually design their own boards and pins. So both of these are nested data structures. And then the last thing I just want to share is a little bit about the types of considerations that you need to think about as you are approaching this data with relation to individuals' anonymity. So in order to identify or to protect identification of individuals online, we follow this idea of contextual integrity, which means that you need to consider how individuals, when deciding to post particular resources or information online, would consider their information to be used. And then also whatever the privacy agreements are of the particular site or data that you're using. So how information flow could threaten the norms of that individual is something that is considered when you're thinking about the overall contextual integrity of a particular situation. And so for us, as we were approaching this, we de-identified across all of these data sets in multiple ways so that an individual could not be connected even though these were already de-identified, we re-de-identified them so that the census data and the ACS data could not be connected to individual teachers' Pinterest data or their school district rasters. Again, even though those were public, we thought that the informational flow that the teachers might consider as they were posting this would not anticipate being connected across all of these sites. So we de-identified. We have 4 special issues, 3 of which are out and 1 more forthcoming this spring. I put the numbers of the volumes and issues here, and I'm happy to take any questions. But also check out this link. It's a nice little AERA presentation we did for one of our seminars. And thank you so much for your time.
Thank you so much, Kaitlin. That's a great presentation. I've learned so much about the use of social media in the classroom. Along that line, though, one of the questions that came up is about using the influence of artificial intelligence, AI, in marketing and things. So are people, can you speak to that a bit more, and how can we say that people are authentically visiting sites without without this influence, or can you control for an influence?
So it sounds, I'm going to answer 2 questions about AI, because I think the question that you suggested was more about like artificial presence, like trolls potentially, or can we identify if these are actual people? But there's also the AI component of being able to use like machine learning algorithms to more efficiently and at scale identify things within social media. So you could use that to identify like particular topics of information being shared, and that's been done by Alan Daly and Josh Rosenberg and others in Twitter. You could also use it, like we have a paper coming out to identify the cognitive rigor of mathematics instruction. So trying to use images and the features within them to be able to scale the identification of cognitive rigor. But there's also AI that then is used to promulgate information by robots. And there are ways that you can figure out if someone is a person or not. Sometimes it relates to like how many posts are being posted, for example, in rapid succession. It can also mean like what is a reasonable number of things that one human could actually post versus like looking at if somebody, a person, but it's not really a person, is posting in all of these different echo chambers at the same time and trying to triangulate the behavior of individuals like that People also use social networks online, but the same types of approaches that Ken has shared today to identify the networks of robots. There are actually networks of robots that try to spread misinformation, unfortunately, within social media. So those are just two things that happen.
Great, thank you, thank you. Another one, sort of along the same lines about use of AI, artificial intelligence, to create individualized experiences for each user. Is there?
Oh, so like an adaptive experience for each user.
Yes.
So, yeah, that's really, there's much work going on in that area. My colleague, Jillian Tang, who's not part of this presentation today, but is part of the fellowship that we're doing over the next several years. And Ken and myself went to an artificial intelligence conference last January. And a lot of what's happening, that we had a social media and education and AI seminar there, but a lot of the work that's being done in that area is actually being driven by computer scientists. So we don't hear about it, I don't think, as much in our journals, but there is a lot of work going on in adaptive approaches to users' engagement and adaptive approaches to students' learning. So I think it would be great to highlight more of that in our journals within Ed.
Thank you. Well, I'll tell you what, why don't this has been really a great webinar with everyone being on today. This is just, and I'm so glad for thank our faculty and to give them a sort of a big hand for joining us today and staying on, everyone, for this time. As we said, we will have a post discussion. I have put something in the chat about that. So it is 4 p.m. Eastern. Can we take a break, and those faculty members come back and others come back at 4:15? I'm going to share my screen here and the link to our post discussion meeting, where you actually we'll have a moderated discussion. You'll get to actually be seen and ask questions to our instructors. That's in the chat as well. And we can come back at 4:15. And any parting words from any of the instructors? Anything else want to say? Well, if not, thank you all again. And I know that your institute is you have activities that will be going on this summer, that you have a website that people can refer to, and we encourage all our participants to do that. And with that, we'll see those who want to join us at 4:15 in the Zoom meeting.
You did great! Exclamation point, exclamation point. I'll be back in a few minutes.
Great, thank you, Ken. We will see.
Oh yeah, we're going over to the other link, right?
The other link into our other room, where we'll meet with participants there.
I think I can't stay for the afterglow meeting, but I would be happy to answer emails if people want to send any comments or thoughts along.
And Kaitlin, there were a couple that came up in chat that I responded to.
Oh, thank you.
There are a couple of deep questions about the quality of the math content and the cultural representations. And I pointed them to some of your stuff. And then you said it a couple minutes later.
Okay, great. Thank you. Yeah, well, it was really great presenting with you all. Thank you for giving us the time today, George. It's nice to meet you.
Nice to meet you as well. Thank you so much for taking time to do this with us. And I hear you're off and off, but I'm glad you were able to do this. I know we'll call on you hopefully in the future. We're all in person at an
That sounds
annual
great.
meeting.
That sounds great. I think I'm actually doing a social media presidential session at ARA this year. So hopefully I'll see you there maybe.
Yes, definitely. I'll make sure to come by on the platform.
Okay, take care, guys.
Take care. Thank you.
Good to
See
see
you
you
at the
all.
next link.
Thanks,
Okay,
George. Bye.
Thanks.
bye.
So I guess we'll leave